And then we can have a further look onto this task 21 that we already solved with using a delta star transform and using a star delta transform. And in each case, we calculated this value here of around 2.1 ohm for the equivalent resistance between the nodes A and B. And so another idea would be to use nodal voltage analysis for this circuit. What we, I think, have also somehow done in the lecture. But still it might not be a bad idea to do it once again. So how can we use nodal voltage analysis to calculate the equivalent resistance of this circuit here? We first need a reference node, and what we also need is we need something to excite currents and voltages in the circuit. And so let's say at first what we need is to have a current source that I will connect like this. And let's say the current source pushes a current to the left side that then goes to the right side through the circuit. So we will get a voltage drop across the circuit, a voltage between these nodes A and B. And if we have a source current here, our equivalent resistance that we would like to calculate at the end, maybe I can write this in this space here. So RAB would then be, how can we then calculate the equivalent resistance? Just divide the current, the voltage by the current, right? Okay, and so now what we need to do with nodal voltage analysis is to calculate this voltage here. And so for this, it would be a nice idea to select this B as a reference node. So I will draw a small ground symbol here as an LT spice and maybe skip the B here and say this is our node 0. Okay, so we have selected the reference node. The next step in nodal voltage analysis was?
Like those three voltages that we have to reduce?
Yeah, we need to number the other nodes. So let me take a different color and maybe number this as 1 and this as 2 and this as 3. And so then the next step is setting up the system of equations in matrix form. And as we have 3 nodes, we need to have a 3 by 3 matrix. With the coefficients, then we have the vector of our unknowns and we have the vector of the sources. And the unknowns are our 3 nodal voltages that always point from each of these nodes to the reference node. Maybe I will take a different color once again to mark them. So the voltage here that points from 1 to 0, this is the same as the voltage that we are looking for. Then this would be the second voltage and this would be the third voltage here. That are there, but at the end that we're not really interested into. So we just at the end would like to have this very first voltage here. Okay, I'm not sure. Maybe I should, to avoid further confusion, say this is V. Okay, so then we need to fill this matrix. What was the rule to fill, or what were the rules to fill this matrix? On the main diagonal,
The sum of each conductance.
we have the sum of the conductances that are connected to each node. So we can check at node 1 we have,
R1 and R2.
yeah, so I need to write G1 plus G3. At the second node we have G1 plus G2 plus G5, and at the last node we have, at this one here we have G3 plus G4 plus G5. Okay, then
We had minus G1, minus G3, and minus G5, I think.
yeah, so now on the off-diagonal elements, we always have the conductance of the connecting or coupling resistors between two nodes. So between 1 and 2 we have R1, so we have minus G1, they are always negative in this case. Between 1 and 3 we have minus G3, and between 2 and 3 we have minus G5. And so this is also what we have here mirrored to the other side. So now our matrix is full, and in the source vector we have always the sum of the sources that are connected to each node, positive if they are flowing towards the node and negative if they would flow away from the node. And we have just this one source that is connected to node 1, so we have just the source current and 0 and 0. And okay, this current source is also flowing away from the reference node, but there is no zeros line and column in this equation and no zeros entry here. So yeah, the reference node, remember, was the dependent equation that we have thrown away, that is not part of the equation system anymore. Okay, so yeah, then I would say, just would need to convert all our resistances that we have into conductances. Yeah, so for n equals 1 to 5. Fill this matrix, solve this matrix, get our nodal voltages and insert them into this equation. And this is, of course, what we will once again do in Octave. So here's my Octave window. Let's move it down here. And yeah, so I will now write all the resistors in just one vector, because then I can do the calculation very simple, and convert them into conductances, which makes sense that we have 1, 1 over 2, 1 over 3, 1 over 4, and so on. So then we can fill the matrix for this nodal voltage analysis matrix. And there we have the following entries. That is G1 plus G3. Then we have minus G1 minus G3. In the next line we have minus G1, then we have why it's not? I don't see what I'm typing. G1 plus G2 plus G5 and minus G5. And the last line is minus G3, minus G5, and G3 plus G4 plus G5. Okay, and then the matrix looks like this, which does not look too bad. At least it's a square matrix and it's symmetrical. and all the off-diagonal elements are negative, and the main diagonal elements are larger than the off-diagonal elements, and so this could work. And so then we need to have our source vector, and inside the source vector we need to have the current source, and the current source is just 1. So inside the source vector we have the current source and 0 and 0. And this is our system of equations. Then how do we solve it? I don't have my t-shirt, but we take the formula from the t-shirt. So we get our nodal voltages from this matrix and the left division with the source vector. And so then we get our 3 nodal voltages, and the first nodal voltage, and it's okay, dividing by 1 does not change anything at the result, but if we would take the first of these nodal voltages and divide it by the source current, what is the formula that is written here on the left side? And then we get the very same equivalent resistance that we had before. So also in this case, we get that V10, which is the same as VAB, is 2.0946 volt, and that's why we also get 2.0946 ohm in this case for the equivalent resistance. So this is also, if you know how to set up this equation system, and if you have something like Octave, MATLAB, Python, a nice calculator to solve the system of equations, if you don't have to do it by hand, then this is also a very efficient and nice way to solve this problem in calculating the equivalent resistance of this circuit. What questions do you have?
Can this matrix be solved on a calculator?
Say again?
Can this matrix be solved on a normal calculator?
Depends on your calculator. So I never have a calculator with me. So my calculator that I used at school definitely could not do it. But it was a calculator that had just one line in a display, or that could just display numbers in a display. If you have such a calculator that has a dot matrix display that can also display fraction bars and functions and so on, then probably it can. And then it's just a question that you need to find out how it works, but there are probably several YouTube tutorials available on how to do it, where people show how it's done with and so if you have some modern Casio calculator or some Texas Instruments, they should always be able to do it.
You can also set up the system from the matrix.
Yeah, and so we could also do it by hand here, but with but I would say everyone should be able to solve it by hand, but in the real life, no one ever really does. But the problem, of course, is if you are unsure how to do it with the computer, and if you have no way to check the result, also what your calculator has calculated, then you have to blindly trust your calculator or the computer program. And so, in our case, once again, we have calculated this with 2 different methods before, this one and this one, and we always got the same result. So it would be very strange if now the solution here was wrong, but still would give us the same result. But then this is this old saying that a colleague of mine, he studied physics, and they had this saying in physics that the number of mistakes always needs to be even, so that 2 mistakes can always cancel each other.